Okie dokie. This problem is awesome. The last two problems are going to use what's called the Nernst equation, not the nerd equation. I mean, if you're using it, you probably are a nerd, so you could call it the nerd equation. And I am proud to be a nerd. I'm a nerd, and I'm proud. Boom. The Nernst equation has to do with, well, what if you don't have solutions at standard solution conditions? In other words, 1 molar. This chart is all about 1 molar solutions. What if we don't have 1 molar solutions? Life isn't all about 1 molar solutions, you know. Can it be? No. All right, so what would happen? We would use this equation. Don't worry about where the derived, how it got derived. It drove a car here. It got derived. Don't worry about that. We're just going to have to use it, okay? Calculus derived, all that stuff. So this equation is going to be used to calculate the voltage produced under non-standard conditions. Notice there's no naught here. That's a 0. We're going to have to take the standard condition voltage produced and subtract all this kind of adjustment factor. All right, well, let's take a look at this problem and see how much voltage would be produced by this, where's my sheet? This, I got the wrong one. This battery, this galvanic cell. Now, what are we going to use in this galvanic cell? We're going to use lead and we're going to use hydrogen. Hydrogen fuel cells. Think of the future. Invest now, invest now. Okay, so what is the EMF voltage of a cell, battery, consisting of a lead and hydrogen combination? Okay, now this is not written like the last problem where everything was set up with the lines and the double bar and the lines. It tells you who got oxidized and who got reduced by the setup. This is not doing that. This is just saying you got lead and hydrogen in a cell. What would happen? Who would get? How much voltage would you produce? You're going to have to figure it out. Who gets oxidized and reduced? How do we do that? Look at the chart. Find lead, find hydrogen. Who's higher? Higher on the chart gets reduced. Lower on the chart, oxidized. Okay, we find lead and hydrogen, the two things we're looking at. Hydrogen, ooh, boom, hydrogen gets a big fat 0. And lead is just below it at negative 0.13. So hydrogen and lead are right back to back here on the chart. Hydrogen's higher. Hydrogen would get reduced. Lead would get oxidized. Okay, knowing that, we are now going to write the reaction in the correct way. So lead, okay, and hydrogen. We're going to get lead and hydrogen. We got to write them in the correct way. We got to show which one's being oxidized, which one's being reduced. Now we know that the lead becomes oxidized because it's just below the hydrogen. So lead becomes oxidized. Oxidized means you go to a higher, so that's a 0, to a higher oxidation number. So the lead would be going from lead atom to lead ion. That's an oxidation. We know it's going to get oxidized because it's below the hydrogen. The hydrogen undergoes the reduction. So the hydrogen's number was an ion, and there were 2 hydrogens, and we have that written down over here. 2 hydrogens, and it becomes the hydrogen atom, well, the diatomic molecule is what it is, with no charge. So we go from a higher value, higher oxidation, to a lower oxidation state. And that's the way it's written right here on the chart, too. If you're not sure, how do you know that? It's written right here for you. You got the hydrogen, 2 hydrogens, and it becomes hydrogen gas. So it's right there. So this is the correct equation. You are going to have to figure that out. Oh, I'll give you one of these. I will. And you'll have to, the ones I give you, the two things, metals that I give you, you are going to have to figure out how to write the reaction. And you know that by looking at who's oxidized, who's reduced. Put down the 2 things. The oxidized goes from lower to higher. Reduction goes from higher to lower. And that is written correctly. And why do we need that reaction? Here's why. That's a Q. Oh, you've seen them before. Q values. They're K values, but at the start. So Q's are K's. Remember, those K values we've been doing all semester. Q's are K's at the beginning of a reaction. So that means a Q and a K are done very similar. They're done the same, actually. products over reactants. Products over reactants. Remember, Q's and K's are products over reactants. You remember that. And so that's why we need the reaction. Products over reactants. Well, let's go ahead and do this problem. We're going to start filling some stuff in here. Now, the first thing I'm going to fill in, I need to figure this out, is I need E under standard conditions. What would be the voltage produced by the cell under standard conditions? Well, we're going to have to pull in what we were just doing earlier. E under standard conditions of the cell is going to be E at the cathode minus E at the anode. So E under standard conditions is E at the cathode. Cathode is a thing that undergoes reduction. Reduction. Who underwent reduction? The hydrogen. The hydrogen was higher. Its number value is 0. So that goes in as 0. Minus the E at the anode, thing undergoes oxidation, that was the lower one, that was a lead. And the lead's number, negative 0.13. Negative 0.13. So if I do the math, I could get how much voltage, how much energy this cell would produce under standard conditions, 1 molar solutions of both of these, and I would produce, subtracting a negative, a positive 0.13 volts. Not very much, but I would get a positive number out of it. I'd produce a little bit of voltage. So that would be the E under the standard conditions. That goes here. That goes there. Okay, so I'm going to go ahead and put that in. 0.13. Okay, we've got that part. We're going to keep moving to the right. Boop, 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 boop. Fill stuff in. Got that figured out. E under standard conditions. Okay, good. Okay, now 0.0257, well, is the number, divided by N. N is the number of electrons involved. The number of electrons involved in the oxidation reduction exchange. How do you know that? Well, look at the chart. We'll just look. How many electrons are being exchanged here with hydrogen? 2. How many with lead? 2. That's and most of the vast majority of these are going to be a 2 on that part. Most of them are based on 2 electrons shifting back and forth between the oxidized and the reduced. So, when in doubt, choose 2. But it is 2 because it says so right there. The hydrogen has 2 electrons and the lead has 2 electrons. 2 goes right here for this reaction. Okay, so that is 2. Now I need the natural log of Q. Q, okay, remember, Q is like K. So I'm going to put K. It's not K. K is at equilibrium. Q is at the beginning of a reaction. But they're done the same way. Products over reactants. Products over reactants. Products. Okay. Lead ion. Lead ion. And what about hydrogen gas? Yeah, that goes in. Okay, over reactants. Okay, reactants, lead. That's a lead atom. That's lead solid. It's solid lead. I mean, don't believe me. It's already on the chart. It's lead solid. Do we put solids? Do those have concentrations? No, remember? See, this chemistry doesn't go away. It's why we learned all that stuff earlier. No, it doesn't go away. There is no concentration for a solid. It doesn't go in the equation. It doesn't go in the K expression or Q expression. What about this one? Yeah, that goes in. These are ions. Okay, that's here we go. Look at. Yeah, aqueous. They're in water. Those would be like the acid has hydrogen ions in water. That goes in. Now be careful, because remember what you're supposed to do with coefficients. So this has to be balanced, and it is balanced. 1 lead, 2 hydrogens, 2 hydrogens. Those become your exponents. Okay, don't forget that. See, this stuff doesn't go away. Okay, that is my Q expression. That is this. Now, I'll get rid of my Nernst. So I'm going to go ahead and put this here, but I'm going to put the numbers in here. up there. I'm gonna put those numbers in. Well, let's see what the numbers are. Actually, I wrote a couple of them right here. I forgot to write that down. Pressure of the hydrogen is, I guess I didn't save myself a whole lot of time. I didn't write them all down. 1 atmosphere. Okay, these are what are given in the problem. So we wrote those down. Let's put those in here, put them in our equation, and solve the equation. So the Q value here would be equal to lead ion concentration. What's my lead ion concentration? Lead ion, that should better be lead ion, not lead. Yeah, it is. Lead ion concentration, okay, lead ion concentration, 2 positive, is 0.1 molar. So that's the one of the problem. The lead ion concentration is 0.1 molar. That goes here. Okay, what is the hydrogen? That would be diatomic hydrogen gas, and it is. You can see on the chart, your reduction chart, it's hydrogen gas. So what is that? Well, remember, we can put we don't have to put concentration, we can put pressures in here. Remember that? We can put pressures in as well. And the pressure of the hydrogen was given as 1 atmosphere. That can also go on the Q or K expression. So we can go ahead and put that 1 in here for the pressure of the hydrogen gas. What about the concentration of the hydrogen ion? Do we have that? Yes, we do have the concentration of the hydrogen ion given as 0.05. 0.05. Don't forget you have to square that because of the coefficient becomes the exponent. There it is. That is your setup. Okay? We needed to go through, I erased it, we needed the E cell at standard conditions to figure that out to put it here. Yeah, we did that. Then we needed to write the correct reaction for what was happening based upon our chart. Hydrogen was higher, so it got reduced. Oxygen was lower, got oxidized. So I had to write that correctly. Why? Because I need this to do the Q expression. So I had to do that. There's a lot of stages to this problem. I like it. I'm telling you. Like it. And now we can do the math and solve the problem and get this over with. All right, do the math. Do the math. Do the math. Do the math. Actually, I did this math out earlier, so it should be here. Where are you? Where are you, math? Where are you? Shane, come back, Shane. Where are you, Shane? Shane, come back. It was a movie. It was called Shane. Check it out. Great Western. This divided by 2 is 0.01285. Okay, minus that. And this natural log of all this stuff. So all this stuff comes out to be 40. Say 0.1, this is 0.02. Opponent that's 0.0025 goes into 1. Yeah, it's going to go 40 times. Okay, 40. This comes out to be 40. So keep going. 0.13 minus 0.01285. Natural log of 40. Do it. Hit it on your thing. LN button, 40, enter. You should get 3.69. All right. Multiply those. Get a product. That product will be 0.0474, 0.0474. Now subtract, and finally, that minus that gives me, we should get 0.083. 0.083 volts. So the amount of voltage produced by these weak concentrations of hydrogen in lead in my galvanic cell would produce 0.083. If they were under standard conditions, we would have provided 0.13. So it is less. They're weaker solutions. So they weren't 1 molar. They were smaller, less, more diluted. So there's not as many ions, not as many electrons being exchanged. Makes sense. Voltage should decrease. And that's what happened. Okay, one more. What?